Hi. So a professor of mine posted this question up on our Facebook group for Temple Engineering, and I figured that I'd just go ahead and record my solution for this. So this is a solution I came up with. I'm pretty sure it's correct, or if it's not totally correct, it's at least pretty much on the right track. So I'll go ahead and just kind of go through this. So the question is, suppose you have a coin which may or may not be fair. Its probability of coming up heads is P. The coin is flipped 10 times and comes up with 7 heads. What is the probability that the coin is reasonably fair? Say P is between 0.45 and 0.55. So the way I'm going to solve this is using Bayes' theorem, which says that the probability of an event A given that event B has already occurred, is equal to the probability that event A will occur times the probability that B will occur given A divided by the probability of event B occurring. So in this particular situation, I'm going to say that event A, so A is the event that we have a coin where the probability of getting heads is between 0.45 less than P and P is less than 0.55. So that is going to be event A. Event B, choose a better color. So event B is going to be the event where we get 7 heads out of 10 flips, out of 10 flips. So basically, if we rewrote this Bayes' theorem equation, it would be the probability that we have a coin where P is between 0.45 and 0.55, given that we have gotten 7 heads out of 10 flips, is going to be equal to the probability of our picking a coin between that has a fairness between 0.45 and 0.55 multiplied by the probability that we will get 7 heads out of 10 flips given that we have a reasonably fair coin divided by the probability that we will get 7 heads out of 10 flips in this universe. So one thing that you might kind of realize right now, um, looking at the question, is there's one piece of information that we kind of really don't know. So the probability of event A occurring. So event A is saying that we have some probability of picking a coin that is fair or that is reasonably within this fairness band. So we don't necessarily know, at least not from this question, what exactly this universe looks like in terms of what the distribution is of coin fairness. So what I'm going to assume for the purposes of this video is that we have a universe where we have a uniform distribution of coin fairness. So what that means is that if I have my probability distribution function and my coin fairness P right here, so coin fairness can range from 0 up to 1. 0 is a coin which never shows heads. 1 is a coin which always shows heads. And my PDF here is just going to be uniform. It's going to be for any different P between 0 and 1. We have an equal amount of probability for choosing that P. So and that uh, probability density function, the height of that is going to be 1. And if we want to figure out what the range or what the probability is of selecting something within our given range, so within 0.45 and 0.55, so 0.45, 0.55, we would just integrate that PDF. So we're going to integrate from 0.45 to 0.55 the function. The function is just 1 dp. And this is pretty easy to see just because we're going to be getting this area in here. So our area here is just going to be 0.1. So in this universe, if I make this assumption that we have a uniform distribution of coin fairness, the probability that event A will occur, that we will get a coin within this fairness band, is equal to zero point 0.1. So that is probability of event A occurring. Now, I could say that that probably isn't a very good assumption to make. I would say that in a more realistic universe, the probability distribution function probably looks something more like that. It's probably normally distributed between 0 and 1 with some standard deviation. It's probably very tightly coupled right around the median point of zero point 0.5, saying that we have a fair coin. For the purposes of this problem, just because we don't have a given standard deviation given in the problem, I'm just going to make the assumption that we have a uniform distribution of probability for selecting either a fair or an unfair coin. But I should say that that's probably not a good assumption for any reasonable universe. In real life, you should hopefully know that the probability of selecting a fair coin is going to be much higher than 10% of the time, which is what this is saying. So anyway, that is our PA with our probably incorrect assumption that we have made here. The next thing that we're going to do is go ahead and actually we're going to work on um, our probability of getting 7 heads out of 10 flips. So in order to do this, we're going to be using the binomial distribution to compute this probability. And that says that the probability of basically having X number of successes out of N trials. So probability X sub N, where we are going to be looking for X successes out of N trials, is going to be equal to N choose X times the probability of us having a successful trial raised to the x. So this is essentially it's the probability of us having a successful trial raised to the number of successful trials we have, multiplied by what is essentially the probability of us having a failure trial. So that's going to be 1 minus whatever the probability is of us having a successful trial, raised to the number of failure trials that we're going to have, which is going to be n minus x. So in this situation that we've got, n is going to be 10 because we're going to have 10 trials, and we are specifically looking at the situation where x is going to be 7 because we're trying to get 7 heads out of 10 flips. So if I simplify this down, n choose x, that's going to be n factorial divided by x factorial times n minus x factorial. Now, if I simplify that down and put in 10 and 7 here, I am going to get 10 factorial divided by 7 factorial multiplied by 3 factorial. And this is going to simplify down because you can see that if we multiply out 10 all the way down to 1, we're going to basically be canceling out 7 down to 1 in our denominator here. So this is going to simplify down to 10 times 9 times 8 divided by our 3 factorial, which is 3 times 2 times 1. And then this is going to simplify down to 120. So I did a little bit of that math beforehand. So if I then work the rest of this out, we have that the probability of us getting getting 7 heads out of 10 flips is going to be equal to 120 times the probability of getting heads, so p heads, raised to the 7th times 1 minus probability heads raised to 10 minus 7 which is 3. So now if I go ahead and simplify this even further, I am going to get that this probability is equal to 120 multiplied by p to the 7th, 1 minus p to the 3rd. And then if I expand this out, I'm going to get p 120 p to the 7th times 1 minus 1 minus p raised to the 3rd. If I go ahead and multiply that all out, I'm be left with 1 minus 3p plus 3p squared minus p to the 3rd. And then if I go ahead and multiply in that p to the 7, I'm going to be left with 120 times, sorry, 120 times p to the 7th minus 3p to the 8 plus 3p to the 9 minus p to the 10. So now what I'm going to do here is keep in mind we have to, for PB here, for our denominator of our function, we have to figure out what is the probability of getting 7 heads out of 10 flips for any probability in our universe. So it's kind of like saying, what is the average probability of getting 7 heads out of 10 flips? So basically what I'm looking for is the average value of this function between 0 and 1. So I can compute that by taking the integral of that function. So the integral between 0 and 1 of 120 p7 minus 3p to the 8 plus 3p to the 9 minus p to the 10 dp. And one thing just to keep in mind, I'm looking for the average value here, but if I do this integral, this is going to give me the area under the curve of that function, not necessarily the area here. So what I have to, or it's going to give me the area under the curve, not the average. So if I want the average, what I have to do is I actually have to divide by the width that I'm integrating over. So in this situation, I'm integrating over width 1, so I essentially have to divide the function by 1, which isn't going to change it at all. So if I go ahead, so I can kind of ignore that for right now. There is an integral coming up though in the solution where I cannot ignore that though. So if I go ahead and do this integral, let me just find where it is. There it is. There it is in my notes. So if I go ahead and do this integral, it is going to give me 120 times p to the 8 over 8, p to the 8 over 8 minus 3 over 9, p to the 9th plus 3 over 10, p to the 10 minus p to the 11 over 11. And I have to evaluate that between 0 and 1. So really all I have to do is just evaluate this function at 1. I'll show you this in later on in the video. I'll bring up Matlab and actually evaluate this out, but I've evaluated it out already. And this comes out to being equal to 0.0909. That's a 0. 0.0909. So we have now got, I believe, 2 values now for our 3 different values to evaluate Bayes' theorem. We've got our 0.1 for our probability of event A. We've got 0.909 for our probability of event B. The last thing that we have to do is compute what is the probability of getting 7 heads given that we have a coin in this probability range. And the way we're going to do that, we're going to evaluate that same binomial distribution that we evaluated earlier. We're going to do this same integral. But now instead of going between 0 and 1, we're essentially going to just integrate this between our probability ranges. So let me go ahead and actually put in that probability range here. So this is going to be the integral between 0.45 up to 0.55 of 120 p7 minus 3p to the 8 plus 3p to the 9 minus p to the 10 dp. And now what you can hopefully see is that what we're looking for is the average value of this function over this range, right? We're looking for between 0.45 and 0.4 and 0.55. What is this average value? So if I just do this integral as it stands, I'm not getting that average value, right? I'm getting the area under this curve. So now this is the situation where in order to actually get this average value, we have to divide by this width. So this is a width of 0.1. And now if we go ahead and evaluate this, we'll basically get this same exact expression here. I'll maybe skip a step because it's really going to be the same integral that we got up here, except we're going to evaluate it between 0.45 and 0.55. And what we're going to end up with, and again, this is a calculation that I did in Matlab, and I'll show you this in a second, but I end up with a figure of 0.1182. Let me just go ahead and make sure that that's actually correct. 0.1183, almost correct. 0.1183. So now the last thing that I have to do is basically just go ahead and multiply together all of those numbers. So this is PA given B is going to be equal to our PA, which was 0.1, multiplied by this PB given A that we just calculated, which is 0.1183. And then we divide all of that by our probability of getting 7 heads, the average probability of getting 7 heads in this universe, which is 0.0909, which is again probably not a very realistic universe given the assumptions that we've made. And we come up with our final probability of 0.1302. So about a 13% chance of of uh, of having a fair coin given that we get 7 heads out of 10 flips. Um, and you can see that that number is probably not correct, given the assumption that we have made about our universe, that we have this uniform distribution of probability here. And one other thing I'll just go ahead and show you real quick. I did a quick MATLAB simulation of this, where we essentially run, I guess this is 50 million trials, and we basically have 50 million trials. In each of those trials, we flip the coin 10 times, and we're looking for trials where we have um, the given number of heads that we're looking for. So right now we're looking for 7 heads. And in this trial, we're basically having fair and unfair coins that are uniformly distributed. And when we run all of these trials, we can find out that the probability of having that range that we're looking for, uh, given that we have already gotten that number of heads, comes out to really close to what we calculated, about 13%. You can also see that our other calculations, so these are simulated probability ranges, those also come out to be kind of exactly what we're expecting them. So the probability of us choosing a coin in that given probability range is 0.1, not surprisingly. Probability of us getting the number of heads, given that we are in the probability range, is the exact same integral that we calculated, and the probability of us getting 7 heads out of 10 flips in this universe is also 0.0909. So that's pretty much it. Maybe I'll just run this real quick to kind of show you. This is the script that I use to kind of actually evaluate those, get a numerical answer out of those different integrals. So you can see that these are the results I got here. But anyway, hopefully you enjoyed that video. I know I I guess I like that problem. I thought it was a pretty good problem. Yeah, thanks so much for watching. Please let me know if you have any questions. Feel free to email me or comment on the video or anything. Thanks. Bye.